Okay, so we have looked through the approximation for the bit error rate coming from the union bound, and we have applied it to some general M-array constellations, MPSK, MFSK, and QAM. And now I'd like to see how we can use this set of equations for different modulation formats to come up with a simple metric to quantify the performance of any given constellation. Simple metric. And the simple metric we're going to use is the loss vis-a-vis QPSK, or with respect to QPSK. So QPSK is going to become like our gold standard. This is like a kind of performance that we're very familiar with, we're very comfortable with, and whenever we come up with some other constellation, we'll be, well, how good is it compared to QPSK? So that is the subject of the capsule today's lecture. So clearly the bit error rate versus the signal to noise ratio, or EB over N0, this is the most informative information we can have about our performance of our constellation. And this is what it comes from the approximation of the union bound. We get bit error rate as a function of EB over N0. QPSK, again, is one of the most popular formats. It's extremely robust. It's fairly simple, so it's just like a good trade-off point. So it's very, like I said, very well known. So when we look at loss, we're going to be using it as a comparison to QPSK. So think of the curve of QPSK as a benchmark. In fact, when I provide study sheets for the exam, notes to be used in an exam, what I do is I just give the plot for QPSK, and from that you can infer the performance of any of the constellations I may give you on an exam, and I'll show you how you can do that today. So we're not giving the complete bit error rate curve. We have the complete bit error rate curve for QPSK. What we're saying is that asymptotic performance is what's going to be compared between this QPSK and other modulation formats. So QPSK is going on down as a waterfall. If we're like well into the waterfall, we're not in the flat part, we're down where it's starting to cascade. If we look there, we'll look at the, and that's why I call asymptotic. We'll look at how we can compare the two modulations. So in order to do this, it sort of exploits this idea of the minimal distance as being the key factor in the union bound. Later in the course, we'll see another metric. So this is one simple metric. And when we're using error correcting codes, there's another metric that we will use to compare or to benchmark the performance. So bit error rate through SNR versus SNR, that's like number one. We're looking at one QPSK, and later we'll see another one with forward error correcting codes. So let's start with the union bound, and remember, I'll just recall for you what we found for QPSK. So in the terms of QPSK, this was the equation that we had for QPSK. And we can see that inside of the Q function, we have here a core of EB over N0, and here we have a core of EB over N0. And we can see that the thing multiplying the square root of EB over N0 in the case of QPSK is 2, the square root of 2. So if I take the little d-min as my criteria, then it's the square root of 2 that multiplies the square root of EB over 0. So what am I trying to say? Something very simple here. It's the square root of 2 times the square root of EB over N0. Because little d-min, you know, by definition, it's this little square, it's the square root of 2. And so we're going to use this little d-min as basically the way that we compare other constellations with QPSK. So we saw previously the results for MQAM, and in this case, if I look at what multiplies the square root of EB over N0, I see that there's something that's a function of M. So now I could see how any M square QAM constellation will perform relative to QPSK. So in this case, the little d-min would be, just by inspection, when I look at this expression I have for the bit error rate, that clearly it is the square root of 6 log 2. And of course, it's because I've written m is equal to L squared. And so when I take log 2, the 2 comes out in front. And then I replaced m with L squared. So here's an expression for this general M area. And so in the case of QPSK, I got the square root of 2 because QPSK is a square constellation. So it could also be described by this equation. You get the same results. And I can see now that there's some factor that I multiply by in order to get back to what was QPSK. And so it is this factor that I multiply by that becomes my measure of how it is compared to QPSK. So this is the part that's the same as QPSK. This is the part that's different from QPSK. And therefore, I'm going to define the loss with respect to QPSK as being in dB, so 10 log 10 of this factor under the square root. So if you will, it's minus 10 log 10 of d min squared. And in this case, this is a definition, so this is the loss I define vis-a-vis QPSK, and it's minus 10 log 10 of d min, and if I plug into that this 2/5, I will get about 4 dB as the result. And now I can say this is a result for 16 QAM, and I can plug in any M I want to find out for others. But let's look at this 16 difference. So here in blue, I have the QPSK curve. And like I said, this is well known. And I know that asymptotically, if I go down in the waterfall, if I move over 4 dB, I'm going to find the curve for 16 QAM. That basically, at least down in this area of the curve, they're pretty much the same. It's not a good approximation here maybe, but asymptotically, when the only thing that matters is what's inside of the Q function, and it's not those multiplicative factors in front that matter, in that case, this gives me a good approximation for the performance of 16 QAM. So if I were to slide this 16 QAM curve over, it would just fall on the QPSK. They're basically the same curves, they're just 4 dB apart. So I know that if I use 16 QAM and I want to get the same performance, if I want to get 10 to the minus 7 BER, if I look at QPSK, I need something like maybe 11.5 dB of EB over N0. But if I use 16 QAM, I have to have 4 dB more. It has to be more powerful in order to get the same performance when I'm using 16 constellation points instead of 4 constellation points. So now let's look at 64 QAM. How would I quantify the difference between QPSK and 64 QAM? And I do the math here, and we come out that this is d min squared is 9 over 63, so that comes out to be 8.4 dB. So for 64 QAM, the loss would be 8.4 dB. I go back to my plot, and I can see now that these curves are very distant. So remember, the curve closest to the origin is the best bit error rate, and here, you can see that it's much closer, much better performance. Big loss when going to very large modulation formats. Again, same curve, just at a different point location. 256 QAM, I could plug that in, and I get up to 13.3 dB loss in this case. And again, the only thing I'm doing is I just take this basic formula, and the only thing I have to do is put in this new L, and boom, I have my loss very easily calculated. So here's a question that we could ask. Suppose I know that for QPSK, I have to have 9.9 dB in order to reach 10 to the minus 5. So here's 10 to the minus 5. I look at my curve for QPSK. Sure enough, 9.9 dB. Now, if I want to use 256 QAM, then I know that I would need 9.9 dB plus the loss, 13.3 dB. So instead, I would need 23.1 dB if I was using EB over N0, if I was using 256 QAM in order to get 10 to the minus 5. So that is why if I asked in an exam, 256 QAM needs how much EB over N0 to reach 10 to the minus 5? Well, all you would have to do in that case is look at the QPSK curve, see what it needed, and then calculate what's the loss and just add it. So this would be theoretically, if I was going to go into MATLAB and I was going to plot the two curves, I could plot this equation because the Q function is, programmed into MATLAB, very easy to use. And I would have this equation would be for the 256 version. And, I would get these two lines. And if I set the value 10 to the minus 5, then I could find out that, yes, it's 9.9 dB. And if I actually did the calculation, sure enough, in MATLAB, it would tell me it was 23.1 dB. So this is, like going right back to the Q function and evaluating it instead of using this reference. But of course, like I said, it's going to give you the same thing, and you would see that they were indeed 13.3 dB apart. Okay, so this is an example coming from a previous exam. And in this previous exam, you can see we have QPSK as one of the possibilities. And then to QPSK, we add 4 new points. In this case, instead of having them tiled, they're also a coordinate plus and minus 3, but now we put them on the axes, so a little different. And in this exercise, the question was, for this particular value of EB over N0, 13 dB, to find the error probability. And to do that, how do we determine it? And so the way to figure this out is to, first of all, you have to find the d-min for this. And in that case, once you find the d-min, you'll be able to find out what is the loss vis-a-vis the the QPSK. And when you go through that exercise, you would get 1.97 dB based on the differences in the d-min. And then you could take the QPSK curve and figure out what the difference between these two, what kind of error performance that would give you. In this case, I'll leave it as an exercise. This is a previous exam, but if you go through the practice of calculating what this is, you would find that this minimal distance the minimal distance is given here, and the associated little d-min, so it's capital d-min and little d-min, is given by the square root of 1.27, which is where, if you put it in dB, comes out to 1.97. Okay, let's see if we can answer the question in the exam now. So we have the QPSK curve here as indicated, and for this modulation format, we know that it's about 2 dB loss. And we're interested, so if it was 2 dB loss, my curve would be something like this, 2 dB over, right? And if that is the case, if I have 13 dB, it would be like having 11 dB if I was QPSK, and so I would take for 11 dB and I would say, it's something like 10 to the minus 7. So the answer would be that for this modulation format up here, if I had 13 dB of EB over N0, then I could probably get 10 to the minus 7 as my bit error rate. So just to summarize the results for square QAM, we used the union bound just now. And this is what we found for the results for square QAM. If you do look in your textbook, it's CLAR in Chapter 9, he will have a formula, and to be honest, I have no idea where it comes from. It's similar, but he has a different multiplicative factor in front. I'm not sure where it comes from. Maybe it's even just an error. But in any case, we'll go with our union bound. And as I mentioned, it is possible to get the exact probability of error in the Proacus textbook. So here is a plot of various modulation formats. And in the first case, we have both BPSK and QPSK, because basically if you go back and look at the equations we developed in the binary section and compare it to QPSK, it's just a multiplicative factor, and on the logarithmic log scale you really don't see that factor, and so they essentially have the same performance. They probably diverge if we got to the lower ones, but asymptotically they're the same. Now as we go to the right, the performance, bit area performance is deteriorating, and we can see first we have 8 PSK. Following that we have our 16 QAM, and now if I get to 16 PSK, there's getting a lot of loss. So the same 16 in QAM and in PSK, I'm taking a bigger hit in the circular geometry. And this is not surprising because, again, when I'm constraining myself to have equal energy symbols, and they are all on the same, packed around the unit circle, the bigger it gets, the more crowded it gets, the more susceptible to noise. When I allow myself to have unequal energies, then I can sort of spread myself out on the two-dimensional plane, and because of that, if I just compare the circular and the rectangular or square geometry, this is the difference in performance between the two. Quite significant. And you can see that if we looked at 16 PSK versus 64 QAM, their performance is actually quite similar. So you can see why QAM is an extremely popular modulation format, because you can increase the number of points in the constellation without taking a big hit in the bit error rate, at least compared to PSK. And remember, when I get more bits per symbol, 16 has 4 bits per symbol, 64 has 6 bits per symbol. That means I can just send information faster, so it's more interesting for me. Here's another exam question, and in this case, we're coming back to maybe a previous example I've had where we have the core QPSK, and now of course we're adding ones that keep these distances the same. And in this case, the question is formed. Here's one geometry for 8 QAM. Here's another rectangular geometry for 8 QAM. And the question is, which one is better performance? And what's the, which one's better, what's the loss? So, again, you go through the same exercise, normalizing it, finding the d-min, and then you'll be able to compare the performance. And here's yet another possibility. I think we saw earlier it was the points here that we looked at. And now we're sort of flushing them out and adding some other points. And you can, again, as a typical exam question would be to go through and normalize this and give some idea of the relative performance. So I could ask you to go through all of the calculations to get down to the actual loss vis-a-vis QPSK or a specific point. Or I could just ask which one is better, like this one, and to know which one's better, you really just have to get to the d-min. And which one is better is the d-min, and you could put that in dB also very easily.